Welcome back to the deep dive. We have a stack of documentation on the table today that I think is going to trigger a little bit of PTSD for anyone who manages infrastructure for a living.
It's definitely the stuff that keeps on-call engineers up at night. Or, I mean, honestly, what wakes them up at 3 a.m.?
Exactly. And to get us into the right headspace for this, I want to bypass the definitions for a second and just go straight to the crime scene. We're looking at a specific scenario from the source material. It's 2:00 a.m. The Black Friday rush or, whatever peak event you had is long over.
Right. Traffic has just dropped off a cliff. You're down to maybe 5% of your peak daytime load. The queues are totally empty.
The world is asleep. You're asleep. But your dashboard is wide awake. And if you looked at your Grafana or Datadog, specifically at that moment, you'd see something that just doesn't make any sense. You have 50 nodes running. Specifically, 50 M5.x large instances.
That's a massive amount of compute for 5% traffic.
Yeah.
It's kind of like keeping the entire stadium lighting on for a single janitor mopping the floor.
It's a ghost town, but all the streetlights are on. And we did the back of the napkin math on this. 50 nodes at roughly 19 cents an hour for just that 6-hour window of low traffic. It comes out to about $76 a night.
Which, to be fair, in the context of a huge enterprise cloud bill, that probably sounds like a rounding error. A CFO might not even blink at that, not at first.
That's what I thought too, initially. But then you multiply it out. That $76 is $2,200 a month, just for air, just for idle CPU cycles.
And that's a cost that scales linearly, right? If your cluster is twice as big, we're suddenly talking about tens of thousands of dollars a year.
For nothing. And that's just the financial waste. The scenario in the reading here highlights something much, much nastier lurking in those nodes.
The hidden danger.
A hidden danger, exactly.
Yeah, so imagine your security team pushed a really critical patch, say, 3 months ago. A new Amazon machine image that patches some zero-day vulnerability in the kernel or maybe the container runtime.
A really serious one.
A really serious one. And any new node you spin up gets that fix automatically. That's the whole point of immutable infrastructure. But these 50 zombie nodes, they've been running for 90 days straight. They're just sitting there burning money and running the old vulnerable image.
So you've got this incredible waste, and you've also widened your attack surface. And the core question the sources are asking is, why? I mean, if we have autoscaling, if we have Kubernetes, why didn't the cluster just shrink itself? Why do we still have these ghost nodes?
And that is the mystery. And solving it requires us to stop looking at autoscaling as just, adding stuff when I'm busy. We have to start thinking about the entire life cycle of a node.
Which brings us to Karpenter. Now, I want to be really clear for everyone listening. We aren't just reading the re-edem here. We're trying to understand why this specific tool fundamentally changes the architecture of scaling. Because Kubernetes has had a cluster autoscale, let's just call it CAS for short, for years now. So why do we need this one? Why did the old CAS leave those 50 nodes running?
It's a fundamental shift in philosophy. I mean, the traditional cluster autoscaler was really built for a different era of the cloud. It was built on top of these older cloud primitives like autoscaling groups, ASGs. It was essentially trying to pilot a bus fleet.
Okay, explain that. What makes an ASG a bus fleet?
It's all about rigid capacity. With CAS and ASGs, you have to predefine all your groups. You have to say, okay, I want a group of M5.larges. And if you need a GPU for a machine learning job, well, you have to make a whole separate group just for GPU nodes.
What if you need a different availability zone for high availability?
Separate group. Different CPU architecture, like ARM, another group. You end up with all these different silos of capacity.
That sounds incredibly complicated to manage.
It is. And the scaling logic is so detached. The CAS sees a pod that needs a home, and it kind of has to nudge the ASG's desired capacity number up by 1. Then the ASG blindly spins up a node from its predefined template. It's clunky, it's slow.
And it often leaves nodes underutilized, right? Because if you have a node with just 10% usage, the CAS might not be able to move things around easily enough to feel safe deleting it.
It's scared to touch things. That's a perfect way to put it. It's very conservative.
So Karpenter just throws that whole model out.
Completely. It just gets rid of it. Karpenter stops managing groups of servers and starts managing the individual scheduling needs of the pod itself. It creates a direct conversation between the Kubernetes API and the cloud provider API. No middleman.
So today, we're going to tear apart Karpenter. We're going to look at how it bypasses the scheduler, how it plays this incredible game of Tetris with your workloads to save that $2,200, and frankly, the part that scares people the most, how it actively deletes your servers while you sleep.
The disruption.
The disruption. And we're going to explain why, in this very specific context, disruption is actually the highest form of safety. But first, we have to build the machine. Let's get into section 1, the core mechanics of provisioning.
The setup. Got to start there.
Let's start with the basics of provisioning, but I want to go a layer deeper than, the marketing copy. The standard explanation is just Karpenter sees a pod and makes a node. But mechanically, what is actually happening inside the API server?
So to really get this, you have to look at how the Kubernetes scheduler works. Normally, you create a pod. The scheduler looks at all of your existing nodes and asks, do I have room for this thing? If the answer is yes, it binds the pod to the node. Simple.
And the pod status goes to running, everyone is happy, the app works.
Right. But in our scenario, let's say we have a sudden spike in traffic. The scheduler looks around at those 50 nodes or however many we have and just says full, full, full. It can't schedule the pod. So it marks the pod status as pending, and crucially, it adds a condition to it, unschedulable.
And this is the exact moment where the traditional cluster autoscaler, CAS, would usually wake up, it would check the ASG limits, and maybe eventually dial up the desired capacity number by 1.
Exactly. It's this slow, indirect conversation. CES talks to the ASG then has to talk to the EC2 API. EC2 spins up a node. I mean, you're talking minutes later, maybe, it finally joins the cluster. Karpenter completely shortcuts this whole process. It's watching that stream of Kubernetes events directly. It sees that unschedulable tag pop up, and it immediately intervenes.
So it's not asking an ASG to scale up for it.
It doesn't even have an ASG in most modern setups. Karpenter acts as a just-in-time provisioner. It calculates exactly what that specific pending pod needs right at that moment.
And when you say needs, we're talking about a lot more than just, I need 2 CPUs and 4 gigs of RAM, right?
Oh, way more. This is where the real intelligence comes in. It's looking at the entire pod spec. It sees the resource requests, obviously CPU and memory, but it's also parsing things like nodeSelectors. Does this pod require Linux operating system? Does it require an ARM architecture? It looks at affinity rules. Does this pod need to be in the same availability zone as my database?
And taints and tolerations, which are always tricky.
A critical point. Yeah, if your pod has a toleration that says, I'm willing to run on a spot instance, Karpenter sees that. It takes this entire laundry list of constraints, which can get incredibly complex, and it resolves them against the entire catalog of available instance types from the cloud provider.
This is that rideshare versus bus analogy from our notes. I want to unpack that because it feels really important, especially for the financial side of things.
It's the perfect visualization, I think. Traditional node groups, the ASGs, are like a bus fleet. You, the operator, decide up front, I'm renting a fleet of 50-seater buses. That's your M5.5X large node group. If 51 people show up at the bus stop, what do?
You have to send 2 buses. And you have 49 empty seats on that second bus that you're paying for.
I'm paying for all those seats.
Yeah.
And you can't just send a sedan because you only own buses. That's your rigid instance type definition.
Okay, so how is Karpenter different?
Karpenter is like a massive cloud-scale rideshare network. If one person shows up needing a ride, it spins up a T3.small, that's your sedan. If 6 people show up, it grabs an M5.large, maybe an SUV. If an entire football team shows up, it spins up a huge C5.9X large. It picks the instance type that fits the workload with the least amount of waste or headroom possible.
That implies it has a deep awareness of the cloud provider's entire inventory. How does it know what an M5.X large actually is, or what it costs? Do you have to program all of that in?
No, and this is one of the coolest parts. Karpenter, on startup, queries the cloud provider API directly so. For AWS, it's the Describe Instance Types API. It builds an in-memory cache of the specs, the pricing, and the real-time availability of every single instance type in the catalog.
So it's basically doing real-time arbitrage against the cloud provider's menu.
Effectively, yes. It's solving a very complex bin packing problem in real time. It's constantly asking, I have these 10 weirdly shaped pods. What is the absolute cheapest combination of EC2 instances that can hold them without violating any of their rules?
But wait, I have to play devil's advocate here for a second. If it can pick any instance from the entire catalog, doesn't that risk total chaos? I mean, I don't want it spinning up some U6TB1.metal instance that costs $20 an hour just because a developer forgot to set a memory limit on their little Hello World app.
That would be a very, very expensive mistake. And that's exactly where the node pool comes in.
This used to be called the provisioner in older versions of the API, right?
Correct. Yeah, in the newer APIs, V1, Beta 1, and beyond, they've split the concept into a node pool and an EC2 node class. The node pool is your governance layer. It's the guardrails. It's where you, the platform owner, say, look, Karpenter, you can be creative, but you are limited to this list of instance families, or you are limited to spot instances only.
And you can set global limits, too. Something like do not exceed 1,000 total CPUs for the whole cluster.
Exactly. It's the budget cap for your cluster's resources.
Yeah.
So you give these boundaries, but inside those boundaries, it has total freedom to optimize for cost and performance.
Okay, so we have a machine that creates the perfect node for the job. It's smarter, it's faster, and it's way more flexible than the old way of doing things. But, and here's the big pivot back to our ghost story, if Karpenter is so smart at creating nodes, how did we still end up with 50 idle ones at 2.0 a.m.?
Because provisioning is only half the battle. If you only deploy a perfect provisioner, you just have a really, really efficient way to clutter your house. You need the cleaner. You need to understand Section 2, the philosophy of disruption.
I have to stop you on that word, disruption, because in my experience, if I walk into a meeting with a generic CIO and I say, I want to install a new tool that actively disrupts our production workloads, I'm probably getting fired, or at least getting a very stern talking to.
Oh, absolutely. The word disruption in IT usually means pager duty is going off. It implies failure. It implies an unplanned outage. It's a bad word.
But Carpenter's documentation uses this word constantly. Why embrace it?
We have to reframe it, maybe biologically. Think about your own body, your skin. Your body is constantly shedding old cells and replacing them with new ones. If it stopped doing that, if it tried to keep every single cell alive forever, you'd get sick. You'd get cancer. Stability in a biological system, and I'd argue in a cloud system, isn't static. True stability is resilience through constant turnover.
So we are moving away from this idea of uptime means nothing ever changes, to
Yeah.
uptime means we can survive and thrive through constant change.
Precisely. In the world of Karpenter, disruption is cluster hygiene. It's the mechanism that actively removes the waste, removes the security vulnerabilities, and keeps the entire ecosystem healthy.
So in this model, a static long-running node is actually a bad node, a suspicious node.
A static node accumulates cruft. That's the technical term for it. Logs fill up disk space, memory gets fragmented over time, security vulnerabilities age like milk. You want your nodes to be fresh. So Karpenter's disruption feature is the immune system for your cluster.
And looking at our notes here, it seems there are three main pillars or three main reasons why Karpenter would choose to disrupt or, delete a node.
Right. The three pillars of disruption they are consolidation, drift, and expiration.
We're going to dive deep into each of those, but before we do, there's a universal workflow for this, right? Like, regardless of why it's deciding to kill a node, the how is always the same graceful process.
Yes, and this is so important for anyone worried about uptime. Karpenter doesn't just pull the plug on a server. It performs this very carefully choreographed, very graceful dance.
Okay, walk us through the steps of that dance.
So step one is identification. Karpenter's logic spots a candidate node that should be removed for one of those three reasons.
Yeah.
Step two is crucial. Cordoning.
Cordoning, that's like putting up the velvet rope at a nightclub.
That's exactly it. It marks the node as no entry. It tells the Kubernetes scheduler, do not send any new pods here. This node is closing down. The door is effectively locked to new arrivals.
Okay, so the flow of new work to that node stops immediately. Then what happens to the pods already on it?
Step three is eviction. Karpenter politely tells the pods currently running on that node, you need to leave now. But, and this is a very, very big but, it respects all the safety rules. It won't just kick everyone out on the street if that's going to cause your application to crash. We'll talk about those safety breaks in a bit.
All right, so the pods get their eviction notice.
Step four is rescheduling. Those evicted pods get moved to other existing nodes that have spare capacity. Or, if there is no room, Karpenter triggers that same provisioning logic we talked about earlier to make a new, better-fitting node for them.
And finally, once it's empty.
Finally, step five, termination. Once the node has been completely drained of all pods, Karpenter makes a direct call to the cloud provider API, the delete instance call, and the virtual machine is deleted. You stop paying for it that very second.
So identification, cordon, evict, reschedule, and terminate. It's a full life cycle.
It's the cycle of life and death for a node in a healthy cluster.
Okay, let's get specific then. Let's go to that first pillar because this is the one that directly solves the financial part of our 2.00 AM nightmare. Let's talk about Section 3, Mechanism 1, consolidation.
The cost saver. This is the big one.
Back to our scenario. We have 50 nodes. They're all M5.X larges, all sitting at a measly 10% utilization, total waste. How does the consolidation logic look at that
It
mess?
looks at it like a giant math problem. Karpenter takes a global view of the state of the cluster. It sees those 50 nodes. It then sums up the resource requests of all the pods running on them and sees that the total usage is, roughly 25 CPUs and maybe 75 gigabytes of memory across the entire fleet.
Which is almost nothing spread across 50 large servers.
It's nothing. So it does the math and has this aha moment where it realizes, wait a minute, I don't need 50 M5.X large nodes to run this workload. I could fit this entire workload onto just 7 of these nodes.
It's basically playing Tetris with the pods.
It's bin packing, but it's a very aggressive, proactive form of bin packing. It's constantly looking at all the running pods and asking that question, can I pack these tighter? It's actively trying to eliminate the air in the box to reduce your bill.
Now, I know from digging into the documentation that there are different flavors of this. You can actually tell Karpenter how aggressive you want it to be using the consolidation policy.
Correct. There are 2 main modes you can set. The first one is when empty.
When empty. Okay, that sounds pretty self-explanatory.
It is. It's the most conservative mode. It will only ever delete a node if it has 0 user pods running on it. It smartly excludes things like daemon sets, which are the system agents for logging and metrics that are supposed to run everywhere.
But if there's even one tiny little user pod on that massive server,
Karpenter won't touch it. It leaves it alone.
so that feels very safe, but in our 2.00 AM scenario.
It fails completely. Because remember, our 50 ghost nodes are at 10% utilization. They aren't empty. They each have a few lonely pods running on them. If you're using the when empty policy, you're still paying that $2,200 a month for nothing.
So when empty is basically just a very slow garbage collector, it doesn't actually optimize the cluster.
Exactly. For real optimization, for that cost savings, we need the aggressive mode. When empty or underutilized,
That is a mouthful of a configuration setting.
it is, but it's the power move.
Yeah.
In this mode, Karpenter actively simulates moving pods around. It'll look at a node and say, hey, node 47 only has 2 pods on it. I'm going to simulate evicting them. Now, is there existing spare room on node 12? Yes. Okay, now let's calculate the cost savings.
Wait, it actually calculates the cost. It's not just looking for empty space.
That's a key point. It doesn't just look for empty space, it looks for cheaper space. It asks the question, is the current hourly cost of the cluster higher than the cost of the cluster after I consolidate these pods? If the answer is yes, and the savings are meaningful, it pulls the trigger.
There's a nuance here in the notes about replace versus delete that I found fascinating, because sometimes you can't just move the pods to an existing node, right?
Right. Sometimes all the other nodes are pretty full too. But Karpenter is smarter than that. It might look at a single node that is, say, an M5.X large, which is big and expensive, and it realizes it's only 20% full. It can't move those pods anywhere else, but it can replace the node itself with a smaller one.
So it's actually swapping the hardware out from underneath the running application.
Effectively, yes. It does the calculation. If I spin up a brand new M5.large, which is half the size and half the cost, these pods would fit on it perfectly. So it does exactly that. It provisions the smaller, cheaper node, gracefully moves the pods to it, and then kills the big expensive one. That is replace consolidation.
That is incredible. It's not just scaling the count of your nodes, it's constantly right-sizing the vertical size of your infrastructure, instance by instance.
Exactly. It defrags your cluster to defrag your wallet.
But doesn't this cause, I don't know, chaos? I mean, if traffic fluctuates even a tiny bit, let's say a background job kicks in for just 10 seconds, is it just constantly killing and creating nodes? That sounds like thrashing.
That is a very real concern, and it's a classic problem in autoscaling. That is precisely why we have the stability timer. In the configuration, it's called consolidate after. You might set it to something like seconds or a few minutes.
And how does that help prevent the thrashing?
It creates what's called a hysteresis loop. It tells Karpenter, don't just react instantly to every little blip. A node has to be a candidate for consolidation continuously for that entire duration before Karpenter will actually take action. It smooths out all the jitters.
So if traffic dips for 5 seconds and then comes right back.
Karpenter ignores it. But if it stays low for the full timer like it does at 2.0 AM, then it finally goes to work.
Okay, so consolidation handles the waste part of our ghost node mystery. We're packing the pods tight and saving a ton of money, but we still have the security problem, the old, vulnerable AMI. Consolidation doesn't necessarily fix that on its own, does it?
No, It doesn't. Consolidation is laser-focused on cost and packing efficiency. If the new nodes it creates to consolidate onto are still using the old image definition from the config, or if it just moves pods around between other old nodes, we haven't solved the vulnerability at all.
This brings us to Section 4, Mechanism to Drift Detection, or as the notes call it, the spec enforcer.
I love that name, the spec enforcer, because that is exactly what it does.
Define drift for us in this context, because in traditional ops, configuration drift is when some admin manually SSUs into a server and changes a file, and now it stops matching the documentation.
It's a very similar concept here, but it's enforced entirely by code. Drift, in Karpenter's world, happens when a node's actual reality in the cloud no longer matches its desired specification as defined in your Kubernetes custom resources. And this is a concept that can trip people up because it involves the passage of time.
The day 1 versus day 4 trap.
Let's walk through that example. Day 1. You tell Karpenter, through your node pool and your EC2 node class YAML, I need an M5.large instance running AMI v1. Karpenter creates it. The node is perfect. It matches the spec exactly. Is correct.
Great. Everything's good.
Day 3, you get an email from the security team. Actually, AMI v1 has a critical bug. We need everyone to move to AMI v2. So you go and you update the EC2 node class YAML file in your Git repo to point to the new AMI ID, and you apply it to the cluster.
Okay, so the config in Kubernetes is now updated.
Day 4. That original M5.large node that was created on day 1 is still running perfectly fine. It hasn't broken, it hasn't crashed, it's serving traffic.
No.
But does it match the spec in Kubernetes anymore?
No. The spec now explicitly says AMI v2. The node is running AMI v1.
Exactly. So that node has now drifted. It was right when it was born, but the rules of the world changed around it, and now it is wrong. It's out of compliance.
This is a huge deal for the whole infrastructure as code philosophy. Usually, if you change a Terraform file or a YAML file, it only applies to new things you create from that point on. The old things just stay as they were until you manually go and hunt them all down.
Right, and nobody ever does that consistently. Drift detection makes the old things automatically obey the new rules. And this is the absolute key to solving our security scenario.
Okay, let's dig into that day 4 problem a bit more. How does Karpenter actually know that a running node has drifted? Is it like checking the OS version constantly? Is it SSHing into the machine to check files?
No, thankfully it's much cleaner and less intrusive than that. It simply compares the live running node's configuration against the EC2 node class definition that it's supposed to be based on. It basically creates a hash of the desired configuration. Yeah. If you change a security group ID in your YAML, or you change a subnet, or most importantly, you change the AMI ID, the hash of that configuration changes. Karpenter periodically scans the entire fleet, compares the hash of each running node to the current desired hash, says, aha, node 45, you are using the old hash. You are out of compliance.
That is so powerful because it also stops the other kind of configuration drift where someone manually changes a setting in the AWS console.
Right. If an engineer, in a panic, manually opens port 22 on a node in the AWS console to debug something, and your Karpenter config says that port should be closed. Well, Karpenter sees that drift. It doesn't just try to fix the port. It marks the entire node as tainted, as drifted.
What does it do once a node is marked as drifted?
It marks it for replacement. Now, unlike consolidation, which often just tries to squeeze pods onto other existing nodes, drift usually implies we need a brand new node to fix the underlying problem. So Karpenter spins up a brand new node, which will naturally grab the AMINUW, because that's the current rule in the spec, and then it gracefully drains the old drifted node and terminates it.
This allows for what the notes call fleet management via declaration. That's a great phrase.
It completely changes your job description as an operator. You don't patch servers anymore. You don't run Ansible playbooks to apt-get update across your fleet. You just change one line of text in a single config file. Use image v2 instead of v1. Karpenter sees the drift and orchestrates a safe, rolling deployment of that change across thousands of nodes automatically.
That is unbelievably powerful. It sounds like it basically solves the security patching nightmare that plagues every large organization.
It does. It turns patching from a manual, risky chore into a simple declarative deployment.
Okay, so consolidation handles waste. Drift handles updates and configuration changes. That seems to cover, well, everything. Why do we even need the third pillar?
This is mechanism 3, expiration.
The time to live.
The TTL, yeah. In the config, this is the setting called expire after. You might set it to something like 30 days or 7 days, or if you're really aggressive, maybe even 24 hours. And it's a very simple rule. I don't care if this node is perfectly utilized. I don't care if its spec hasn't drifted. If this node is older than X hours, kill it.
That seems arbitrary. If it ain't broke, why fix it?
Because in complex computer systems, ain't broke is usually just a temporary state of not visibly on fire yet. And frankly, long-running servers are deeply suspicious.
So suspicious in what way?
There are really three main reasons for having a max lifetime for expiration. First, and most obviously, hidden security risks. Maybe the AMI ID in your spec hasn't changed. But what if a new zero-day vulnerability was found in the Linux kernel just 3 days ago? Your node that's been running for 60 days definitely has that vulnerability. A fresh node, on the other hand, often pulls the latest minor patches on boot.
So it's a proactive refresh to catch things that don't trigger a formal AMI update.
Exactly. The second big reason is that cruft we talked about.
You mentioned cruft earlier. Can you give me a concrete example of cruft that could kill a node's performance after, say, 60 days?
Absolutely. You can take a standard Java application. Over time, you might have very minor memory leaks that aren't big enough to ever crash the app, but they slowly eat into the available OS buffer cache, making everything on the node slower. Or file descriptors. I've seen production nodes run out of available file descriptors because a logging agent wasn't configured to rotate its logs correctly. The node isn't dead, but it's kind of zombie walking. It's slow, it's buggy.
So the classic, have you tried turning it off and on again? Strategy is a classic for a reason. Expiration just forces that reboot cycle at the entire infrastructure level.
It is the ultimate turn it off and on again.
Yeah.
And the third reason is maybe the most important from a cultural perspective, testing your recovery processes.
Sure.
If your nodes never ever die, you never actually know if your application can gracefully handle a node dying.
Oh, that's diabolical, but brilliant. It's a forced, constant fire drill.
If you have a node that has been running for 2 years, that node is a pet. You are terrified of it dying because you have no idea what will break. If you force every node to die every 7 days, your engineers have no choice but to build applications that are resilient to failure. It forces that cattle, not pets mentality.
So how do these three mechanisms work together? Is there a hierarchy, an order of operations?
There is, yeah. Generally, expiration takes the top spot in the hierarchy. If a node is expired, its time is up, it has to go. It doesn't matter if it's also drifted or underutilized. Then comes drift. If a node's configuration is wrong, it needs to be fixed. And finally, at the bottom is consolidation. If a node is correct and not expired, but it's just wasteful, then let's optimize it.
And what happens if a node is both expired and drifted at the same time?
Karpenter is efficient. It will just replace it once. The new node it creates will solve both problems simultaneously. It resets the expiration clock, and it will be built with the correct non-drifted spec. 2 birds, 1 stone.
Okay, I'm completely sold on the mechanics. This sounds amazing. But I can hear the nervous listeners out there, the folks running production databases or critical payment gateways on their clusters. They are thinking, you are telling me this piece of software is going to, on its own, decide to randomly delete my servers at 2 a.m. What if it goes rogue and deletes all of them?
It's not random, but yes, it is deleting them, and that fear is 100% valid. You're giving a robot the keys to your kingdom.
So how do we prevent chaos? How do we stop the thundering herd problem, where an AMI update causes every single node to be deleted at once?
This is where we get to Section 6,
Lots
safety
of-
controls. This is where we talk about the brakes on the system, because you are absolutely right. If you update your AMI and you have 100 nodes, and Karpenter suddenly says, oh, 100 drifted nodes, I'll delete them all, your application goes down hard.
A total self-inflicted outage.
To prevent that, we have disruption budgets.
Budgets, you mean like a financial budget?
Similar concept, but it's an allowance for destruction, not spending. You configure a budget right in the node pool. For example, you can set a value like nodes, 10%.
Explain what that 10% actually does in practice.
It tells Karpenter, you are only allowed to be actively disrupting 10% of the nodes in this pool at any given moment. So if you have 100 nodes, it will identify all 100 as drifted, but it will only pick 10 of them to start the cordon and drain process. It will wait for those 10 to be fully replaced and for their replacements to be healthy and ready. Only then will it move on to the next batch of 10.
So it turns a potential cliff, a sudden drop-off, into a safe, controlled rolling update.
Exactly. It throttles itself.
That's a huge relief, but that's protecting the nodes, the infrastructure. We also need to protect the applications running on them, right?
Yes, the pods themselves. And this brings us to probably the most important acronym in Kubernetes reliability, PDB, the Pod Disruption Budget.
I feel like we could do a whole deep dive just on PDBs, but give us the crash course. How does a PDB act as a brake for Karpenter?
A PDB is basically a contract. It's a contract between the application developer and the cluster's control plane. The developer writes a little YAML file that says, for example, my critical web application has 3 replicas running. You can delete nodes, you can reschedule my pods, BUT, at all times. The min available number of pods for this app must be 2.
So it's a way of saying, whatever you do, don't kill me down to my last survivor.
Exactly. And Karpenter respects this religiously. When Karpenter wants to delete a node, it doesn't just kill the pods. It calls the official Kubernetes eviction API. It formally asks for permission. Is it safe for me to evict this specific pod right now?
Walk us through a quick scenario.
Okay. You have a critical payment service. Node A has one pod of that service. Node B has another. The PDB for the service says keep 2 available at all times. Karpenter decides it wants to consolidate both nodes to save some money.
So it starts with node A and tries to evict the pod on it.
Right. It calls the eviction API. The API server checks the math. The service currently has 3 replicas. Evicting one leads 2. That satisfies the PDB. Permission granted. Success. The pod on node A starts terminating and rescheduling.
But until that pod actually lands on a new node and reports back that it's healthy, the count of available pods is effectively down to 2, or maybe even 1 if the other is still spinning up.
Exactly. The system is in a fragile state for a moment. Now imagine an overeager Karpenter immediately tries to touch the pod on node B. It calls the eviction API again for that second pod.
And the API server says,
Nope. It returns a 429 too many requests error, which basically means PDB violation. Karpenter is blocked. It has to wait. It will literally sit there and retry until the first pod is back up and healthy on a new node. Once the replica count is back to a safe level, then it can proceed with evicting the pod on node B.
So PDBs are the fine-grained application-aware breaks for Karpenter's powerful disruption engine.
They are the most important safety control you have. If you don't configure PDBs for your critical apps, you're telling Karpenter it can delete everything as fast as the main disruption budget allows. PDBs are how you, the application owner, tell the robot, be extra careful with this one.
Is there an emergency brake, a way to just say, do not touch this node, ever? You know, for that weird legacy app that takes 4 hours to boot up and you just have to leave it alone?
There is. It's the do not disturb sign for your nodes. It's a simple annotation you can put on the node object itself. Karpenter.sg-not disrupt.
True. And if I put that on a node,
Karpenter will completely ignore it for all disruption activities. It won't consolidate it. It won't replace it for drift. It won't expire it. The node becomes invisible to the entire disruption logic.
it becomes a pet again.
It becomes a pet. A ghost node in the making, created by your own hand.
Right.
It's a very useful escape hatch for emergencies or for very specific stateful workloads. But you have to understand the trade-off. That node will now run forever unless it fails on its own. It will accumulate security flaws. It will cost you money. You are consciously opting that single node out of the self-healing lifecycle.
So use with extreme caution.
Extreme caution should be the exception, not the rule.
All right, we have all the pieces. We have the provisioning, the 3 disruption mechanisms, consolidation, drift, expiration, and we have the safety controls. Let's solve the mystery. Let's go back to 2:00 a.m.
Let's resolve the scene. Time to be the hero.
We have 50 MF5.x large nodes, 10% utilization. They're running an old, vulnerable AMI. Some of them are 45 days old, way past any reasonable expiration. Karpenter wakes up, or rather, its periodic reconciliation loop ticks over. What happens? Walk us through it minute by minute.
Okay, so Karpenter's controller looks at this fleet of 50 nodes and sees a target-rich environment. It sees nodes that are wildly underutilized, which is a consolidation trigger. It sees nodes that are drifted because their AMI doesn't match the current spec. And it sees nodes that are expired because they're older than the 30-day expire after setting.
It's a triple threat. It could kill them for any of those 3 reasons.
So it formulates a plan. First, it calculates that the total current workload could easily fit on just 7 MF5.x large nodes.
That's step 1, the calculation.
That's 1. Then step 2, it provisions 7 new nodes. Why new ones? Because the current ones are drifted and expired. It needs fresh nodes that will be built using the new secure AMI hash and will have their expiration clocks reset to 0.
So 7 brand new secure nodes spin up and join the cluster. The cluster size temporarily goes up to 57.
Correct, for a brief period. Step 3. As soon as those new nodes are ready, it starts draining the 50 old nodes. But it respects the budget. Let's say our disruption budget is configured to 20%. That means it can disrupt 10 nodes at a time. So it cordons and drains the first batch of 10 old nodes.
The pods that were on those 10 old nodes get the eviction notice. Karpenter checks their PDBs, and then they get rescheduled onto the 7 new secure nodes that are waiting with plenty of capacity.
Exactly. And step 4. As each of those old nodes becomes completely empty, Karpenter sends the final terminate command to the cloud provider. 10 nodes vanish from your bill. Then it starts on the next batch of 10, then the next, and so on.
And the final result of this automated process.
Let's fast forward the clock to, say, 4:50 a.m., about 1 hour after the process started.
So our on-call engineer wakes up, grabs their coffee at 8 a.m., and pulls up the dashboard. What do they see?
They see a beautiful sharp cliff in the node count graph right at 4:15 a.m. The total node count dropped from 50 all the way down to 7.
And the CPU utilization on those remaining 7 nodes?
The utilization is now at a much healthier, say 70% or 80%. They are being used efficiently, but there's still headroom. And most importantly, they're all running the new patched AMI.
What about the cost?
The cost is plummeted. We dropped from $9.50 an hour to roughly $1.33 an hour. That is an 86% cost reduction every single night.
And the critical security vulnerability?
Gone. Completely eliminated from the running infrastructure. The attack surface has shrunk by 86%, and the surface that remains is now fully patched.
And the engineer who was on call?
Still asleep. Or, peacefully drinking their coffee in the morning. They didn't get paged. They didn't have to run a single script. The system healed itself.
That really is the dream state for infrastructure management. But trust but verify, right? How do we know all this happened if we were asleep? Let's talk about Section 8, observability.
You absolutely need to know where to look. Karpenter emits a ton of very useful Prometheus metrics. The big one you want to watch is Karpenter Notice Terminated Total. And the best part is it has labels on it for the reason. So you can build a graph that shows, last night we terminated 43 nodes due to consolidation, and 7 nodes were replaced due to drift.
That would be a very satisfying graph to look at over your morning coffee.
It is. It's proof that the system's working.
Yeah.
You can also, of course, look at the controller logs. You'll see these nice structured logs with fields like reason underutilized and action delete. It tells you exactly what it was thinking step by step.
And what about alerting? Because I imagine you don't just want to know when it works. You want to know if something goes wrong with this powerful process.
Definitely. You want to set up a few key alerts. You probably want an alert for high disruption rate. If it's suddenly killing nodes way faster than usual, maybe something is misconfigured. And another really important one is nodes stuck in disruption.
Stuck. What does that mean?
It means a node has been cordoned, but it never successfully terminates. This almost always means a pod disruption budget is blocking an eviction. A pod is refusing to move, and the drain process can't complete. You want to know about that immediately so you can go fix the application's PDB configuration.
Fantastic. So we've taken apart the machine, looked at all the gears, and put it back together.
We have. The ghost is busted.
Let's summarize the key takeaways from this deep dive.
I think there are 3 main ones. First, Karpenter is a unified lifecycle manager, not just a provisioner. It owns the node from cradle to grave. It builds it, it watches it, and when the time is right, it kills it.
Second takeaway.
Disruption is the key to efficiency and security. You simply cannot save money or stay secure in the cloud if you are afraid to delete nodes. You have to embrace the churn. You have to build systems that expect to die.
And third?
The 3 mechanisms, consolidation, drift, and expiration, all work together as this beautiful self-healing loop to automatically handle waste, updates, and general hygiene.
It really is a profound shift in the operating philosophy. And I want to leave our listeners with a final thought that struck me while going through all this material. We are really moving away from the job of managing servers.
We're managing definitions now.
Exactly.
You define in a simple text file, I want secure, efficient nodes. You write that down as your desired state. And the software's only job is to make the messy reality of the cloud match that clean definition, even if that means destroying the current reality and rebuilding it from scratch every single night.
It's a brave new world. It demands more from us as application engineers. We have to write good PDBs. We have to handle termination signals gracefully. But the payoff is a cluster that largely manages, secures, and optimizes itself.
Absolutely. The payoff is huge.
So here's my challenge to you, the listener. Go check your bills. Go check your dashboards tonight at 2:00 a.m. Do you have ghost nodes haunting your cluster? And if you do, maybe it's time to let Karpenter perform an exorcism.
I couldn't have said it better myself.
Thanks for joining us on the Deep Dive. We'll see you next time.